When you think about what makes a device fast, your phone, your laptop, anything, really, what's the first thing that comes to mind?
Well, for decades, the answer was always the same, right? It was the processor, the CPUs.
Exactly, the CPU. We all grew up sort of equating speed with gigahertz and core counts, just assuming that the faster that one central brain spun, well, the faster the computer was.
And that perception, I mean, it was completely accurate for a long time. For the 80s, the 90s, even the early 2000s, that was the whole game. But now, that way of thinking is fundamentally outdated.
It sounds like it creates a total misunderstanding of how modern performance is even engineered.
It really does.
Okay, let's unpack this right away because the
Yeah.
sources we've got for this deep dive, they challenge that whole single brain idea head on.
Hmm.
If you're listening and you think you have a handle on processing power, you might want to prepare for a bit of an architectural shift here. Our mission today is to cut through that old kind of monolithic thinking and really break down the reality of it, which is much more sophisticated. Modern computing speed, it doesn't come from a single powerful generalist anymore.
No, it comes from a team, a highly specialized and actually surprisingly efficient team of processors all working in concert.
So this deep dive is really tailored for you, the listener.
Hmm.
We're going to get into the weeds on the hierarchy of silicon. We're going to understand the core roles, the architectural differences between, the established central processing unit, the CPU,
The old standby.
the now omnipresent graphics processing unit, the GPU, and the newcomer that's becoming more and more vital, the neural processing unit, or NPU.
Or AI accelerator, you'll hear that term used a lot too. They're basically the same thing.
And the core insight we're chasing here, the real takeaway, is this. The speed you actually perceive on your device isn't just about raw power anymore. It's about assigning the right job to the right kind of engine.
That's the whole game now. It's about specialization.
We're moving past the simple labels today and really exploring how these chips differ architecturally, functionally, the why behind the what. And that's where I think the real aha moments are for anyone who follows this topic.
And, to really set the stage here, it's important to understand why this shift happened. The sheer complexity and, frankly, the volume of today's workloads. I mean, think about it. Streaming 4K video, running generative AI models, real-time cryptography, just massive multitasking.
And things we do every day without even thinking about it.
Exactly. And a generalist chip just can't handle all of that efficiently. We literally hit the physical limits, the power and thermal limits of trying to make a single CPU core faster and faster. So the industry's pivot to specialization, it wasn't a luxury, it was a necessity. It was driven by physics.
So now we rely on this specialized hardware to get that overall system speed we crave.
We have to. There's no other way.
Okay, so let's start where computing really started, with the essential generalist, the foundation, the master of ceremonies, the CPU.
The central processing unit, I mean, the name says it all, right? It's central. It has to be the device's general purpose brain. It has to be versatile, adaptable, and above all, completely reliable.
And even though modern chips, they have integrated graphics or AI bits baked in, you're saying the core function of the CPU itself hasn't really changed. It's still the conductor of the orchestra.
That's a perfect analogy. It is the conductor.
So what exactly is its job in a modern system then? When it's surrounded by all these hyper-specialized components, if a GPU can process certain data way faster, why is the CPU still so essential?
Because it's the only one built to orchestrate complex, unpredictable tasks. Its core responsibilities, and our sources really highlight this, are things like running the operating system itself.
EOS, okay.
Yeah, managing memory, handling all the fundamental security processes, and, facilitating that smooth multitasking we all just take for granted. If you're opening a spreadsheet, managing a file directory, dealing with network traffic, that's the CPU at work, coordinating all those infinitely varied tasks.
And the key thing here, the thing we really need to understand, it's the kind of logic it excels at. It's not just about speed, it's how it thinks. And we established that the CPU is specifically optimized for what's called branching logic.
Yes.
The if this, then that, decisions that basically define an operating system.
That is the architectural fingerprint of the CPU, 100%. Branching logic is, by its very nature, sequential and decision-based. For any complex piece of software, you don't. You just can't start the 50th step until you know the exact result of the 49th step.
Right, there's a dependency.
A huge dependency. Imagine the OS scheduler. It's constantly making decisions. If this process is running, then dedicate resources X, Y, and Z. But if the user clicks cancel on a dialog box, then you have to drop all those processes and revert the whole system back to state A.
So those instructions are all over the place. They're sequential, and they have to be perfectly accurate immediately.
Immediately and perfectly. So if I click the save button in my word processor, the CPU is what handles that logic. If the file name is new, then I need to prompt the user for a location.
Which requires a very deep, very fast instruction pipeline to handle that kind of thing without lagging. Right?
Precisely. To handle that sequentially complex workload quickly, the CPU relies on really sophisticated features. Deep instruction pipelines, and crucially, something called branch prediction. It literally tries to guess which path the program will take next.
It's trying to think ahead.
It is, and if it guesses correctly, the process feels instantaneous. But if it guesses wrong, it has to flush the entire pipeline and start over, and that's a massive performance penalty. And that's why CPU cores are physically huge. They're complex. They carry large amounts of ultra-fast memory called cache L1 and L2 cache right next to the core. They are optimized for one thing above all: low latency.
Latency. So getting the single correct answer as fast as humanly possible.
As fast as humanly possible, even if that means sacrificing the ability to do millions of things at once.
And that distinction, latency versus throughput, that is so critical for anyone listening to understand. The CPU gives up the ability to process millions of small calculations at the same time, which is throughput, in exchange for this surgical precision and speed on just one or two complex tasks at a time. Latency.
And that's the manager analogy in action. You've got this highly skilled manager who can do a huge range of different jobs, but they're focusing on only a few variable, complex tasks at a time, and they're processing them sequentially and, with perfect accuracy.
And that complexity is also why CPU architecture leans towards what they call CISC, right?
Yeah.
Complex instruction set computing.
That's right. Those instructions are designed to do a lot of heavy lifting in a single step. It makes the code denser, but it optimizes the performance for these sequential decision-making workloads that the CPU specializes in.
Which brings us back to that fundamental why analysis. Why is this generalist approach still so essential? I mean, if GPUs and these new NPUs are so incredibly fast, why even bother having a CPU at all? Why not just have a giant GPU run the whole operating system?
It's a great question, but the answer is because the CPU coordinates everything. And it handles the unpredictable. A GPU is a mathematical engine. It's a number cruncher. It simply cannot handle the sheer variability and the level of control required to run a full operating system.
So without that reliable manager at the top.
Without that single, reliable, generalist manager at the top, the one controlling the input and output, managing the security stack, deciding which program gets executed next, all those other specialized components, they couldn't communicate. They couldn't function together as a coherent system.
It's the glue.
It's the glue. It's the system's foundational operating logic. It's the only part built to arbitrate the chaos of running an entire computer.
So it makes sure that when the GPU finishes rendering a beautiful frame of a game, that frame actually ends up on your monitor, right where the operating system told it to go.
Exactly. That generalist role is completely non-negotiable for system stability.
Okay, so if the CPU is this complex, highly optimized manager, let's turn to its partner in crime, the graphics processing unit, the GPU. This is where we see that first huge pivot towards specialization and what you call throughput.
It is. The GPU started, of course, with a very clear, very niche purpose: to draw graphics.
Right, pixels on a screen.
Pixels on a screen, calculating the color and position of pixels, rendering textures, projecting 3D scenes. It was a very predictable and, crucially, a very repetitive task.
But the source materials we looked at, they really emphasize that its true superpower isn't really just drawing things. It's architectural focus on massive parallelism.
Absolutely.
Yeah.
And architecturally, the GPU is the complete opposite of a CPU. Where a CPU has a handful of large, complex decision-making cores, maybe 4, 8, or 64 in a big server, a GPU contains thousands of smaller, simpler cores.
Thousands.
Thousands. And these cores, they aren't optimized for branching logic or complex sequencing at all. They're designed to do one thing: perform the same type of operation on vast amounts of data all at the same time.
This is where we shift from that surgical precision of the manager to the sheer brute force of the massive factory floor.
That's the analogy.
The CPU manager is giving highly detailed, unique instructions to maybe a dozen employees. The GPU factory floor has 10,000 workers, and every single one of them is doing a simple, repetitive calculation like multiply this number or calculate the light falling on this one spot.
And critically, they operate under a model called CMD. Single instruction, multiple data. You send one instruction, for example, add 5 to this number, and the GPU applies that single instruction to thousands of different data points, whether they're pixels or vector data or neural network weights at the exact same moment.
So they're terrible at making decisions,
Awful.
but they are unbeatable at repetitive brute force math.
Unbeatable. The scale is what's just staggering. And this massive parallelism, it shines in very specific demanding areas. So beyond just rendering complex graphics, those same parallel properties are perfect for tasks that involve processing huge amounts of image data or video or scientific data.
Because at their core, those are all fundamentally matrix-based operations.
Yeah.
Just big grids of numbers.
Big grids of numbers. And this is where the GPU's role just exploded over the last decade. It transitioned from being just a graphics card to a general purpose GPU, or
GPU, right.
And now, executing demanding scientific simulations like fluid dynamics or genomic sequencing, and most significantly, handling the heavy lifting of machine learning training, all of that relies entirely on this parallel architecture.
The insight there, for me, is that the math you need to shade a single pixel in a video game is fundamentally similar to the math you need to process a single neuron's weight update in a neural network.
That's the common denominator. It's a massive multiplication and accumulation problem.
And if you need to manipulate 1 million of those data points with the same formula, the CPU is just going to chug through them sequentially, or maybe semi-sequentially. It's spending all these precious cycles on control and decision-making.
Whereas the GPU, it operates under the assumption that decisions are minimal. It just processes them in massive blocks all at once. This focus on maximizing throughput is why GPUs have become the undisputed backbone of modern supercomputing and all the large-scale AI training clusters you hear about.
You know, I find that architectural reflection just profound. Moving from a few powerful, latency-optimized cores to thousands of simpler throughput-optimized cores, it fundamentally shifts how we even approach computing problems.
It does. It's an explicit acknowledgement that the efficiency gains in modern computing, they come from matching the problem type to the hardware architecture.
We finally admitted that the generalist CPU was actually highly inefficient for tasks that were intrinsically parallel.
Exactly. Trying to solve a complex matrix problem with a CPU is like using a single brilliant chess master to solve a Rubik's Cube. I mean, they can do it eventually, but 10,000 dedicated simpler hands can do it way, way faster. The GPU allows for that brute force specialized simultaneous work, which frees up the CPU to remain the reliable decision maker it was always meant to be.
Okay, so we've got the generalist manager, the CPU, handling sequential logic and low latency. And we have the parallel factory, the GPU, for high throughput, massive math problems. But computing, and especially the world of AI, it just keeps demanding more and more efficiency.
Always more.
Which leads us to the third crucial player in this hierarchy, the hyper-specialist.
Right. So now we're seeing the rapid and really the essential integration of the neural processing unit, the NPU.
The NPU.
And our sources refer to it interchangeably as an AI accelerator. You'll see major players like Google, they have their own proprietary versions like the TPU, the tensor processing unit, but the function is largely standardized across the industry. This is the newest specialized engine, and it is custom built for one job and one job only.
Which is?
Running AI models with unparalleled efficiency.
Okay, so the GPU was already good at AI, even great. But you're saying the NPU is explicitly designed just to run the core mathematical operations behind AI models. What makes it structurally different from a GPU?
So let's get really specific about the math here. The NPU is optimized almost entirely for matrix operations. You'll hear this called tensor processing. And these are used constantly in neural networks. It's just vast grids of numbers that need to be multiplied and accumulated over and over and over again.
So the architectural difference is that the NPU focuses entirely on those, what are they called, multiply accumulate operations.
MCs, exactly. And it often integrates the memory much, much closer to the computational units, which minimizes the physical travel time for the data. It's all about cutting down on that overhead.
But that still sounds a lot like parallelism, which we just said the GPU handles brilliantly.
Yeah.
So if the GPU is already the parallel powerhouse, what was the engineering need for the NPU? Why create a whole third specialist, especially in consumer devices?
That is the key question. And the primary goal for NPU development is twofold. It's superior efficiency and dramatically lower power consumption.
Ah, power.
Power is everything. When you are training these massive foundation models in a data center, you use incredibly powerful, energy-hungry GPUs. Training demands the absolute highest precision. We're talking FP32 or FP16 floating point arithmetic. And raw speed is everything. Power consumption is, a secondary concern to performance.
But the NPU, it isn't really for training, is it? It's designed for inference.
Yep.
That's the big distinction.
That's the distinction.
Running a model that's already been trained, but running it on a consumer device, like your phone or your laptop.
Precisely. In a laptop or a phone, or even in an embedded system like a smart camera, every single milliwatt of power you can save is absolutely crucial. If you have an AI task like real-time language translation or continuous background noise suppression on a call, and it's running constantly,
Right.
using a GPU for that would just drain the battery in no time. And it
Yeah.
would generate enormous heat, which completely ruins the user experience.
Okay, so the NPU achieves this incredible power efficiency, and it does it partly by sacrificing some of that super high precision that the GPU has. It operates in the realm of lower precision arithmetic.
That's one of the key architectural breakthroughs. AI inference, as it turns out, often doesn't need that perfect 64-bit floating point precision that a big scientific simulation demands. When you're just running a trained model, 8-bit or even 4-bit integer math, you'll see it as INT8 or INT4 is often more than sufficient.
Wait, INT8, so you're talking about integers, not floating point numbers with decimals.
Exactly. And by reducing the size of the numbers it's processing the data path with, the NPU can achieve far, far more calculations per watt. It can reach these phenomenal TOPS figures, tera operations per second, without generating all that heat. It's custom-tailored hardware that just cuts out all the unnecessary overhead that a more general-purpose GPU might carry.
That is a fascinating trade-off. You're basically accepting a slight, often unnoticeable reduction in mathematical precision for this dramatic increase in performance efficiency.
Which is absolutely necessary for any device that runs on a battery.
And this connects directly back to the user experience and increasingly to privacy. This focus on efficiency is what enables what the industry is calling on-device AI or edge AI.
Right. It allows your device to do smart things without constantly having to stream your sensitive data to some massive centralized data center in the cloud.
And that's the critical relevance for anyone listening. I mean, think about the privacy implications of that. If my phone needs to analyze my speech patterns to give me better predictive text, or if it's organizing my private photos by recognizing the faces of my family.
Do you really want to send all that to the cloud?
Exactly. Streaming that data is slow and it's risky. The NPU keeps all that heavy lifting local, fast, and private.
It really does. It lets the device perform really sophisticated AI work, like that complex background blur during video calls or real-time secure authentication or that highly advanced predictive text. And it does it faster, more reliably, and much more privately, all while minimizing the heat and the battery drain. The NPU really represents the future direction of personalized computing.
Less reliance on massive servers somewhere else.
And more intelligence just baked right into the device that you're holding in your hand. Hashtag tag 2.2, defining the best tool for the job, synthesis.
So if we synthesize all of this, we look at these three specialized architectures. The deep pipeline, the CPU, the wide array, the GPU, and this hyper-efficient tensor engine of the NPU. We come right back to that core conclusion from our sources.
That there is no single chip that is best.
It just doesn't exist. The right answer always depends on the architecture of the task at hand.
Which I think finally moves us past that old, frankly lazy marketing language of faster clock speed equals a faster computer. We can now provide a really clear, architecturally driven allocation summary for anyone trying to actually understand their system.
Let's do that. Let's lay out the roles based on those three fundamental architectural priorities we've been talking about: latency, throughput, and power efficiency.
Okay. So the CPU is best for sequential logic, for low latency tasks, and for varied, unpredictable workloads. It's complex, few cores, it's large cache, and its ability to handle that branching logic make it the essential general manager of the entire system.
No arguments there. Then we have the GPU. It's the champion for large-scale, high-throughput parallel workloads. If you need to apply the same calculation to millions or billions of data points, and you prioritize raw speed over low latency or extreme power efficiency.
Like for gaming or rendering or AI training.
Exactly. That is the GPU's domain.
And then the NPU. It is the champion for focused, power-efficient parallel workloads. It excels at those very specific AI operations, the matrix math, especially for inference on battery-powered devices where a minimal thermal footprint and localized processing are the absolute key priorities.
So it trades that general purpose applicability and the super high precision of the GPU for just extreme efficiency.
That's the trade-off.
The insight here is it's profound. This whole trend suggests that future computer speed gains, they won't come from just making the CPU faster anymore. They're going to come from refining this intricate collaboration, making the handoff between the CPU, the GPU, and the NPU totally seamless, intelligent, and instantaneous.
The entire engineering challenge has shifted. It's gone from optimizing a single chip to optimizing the entire system interconnect and the software layer on top of it. That intelligent task scheduling, the software that decides whether a certain calculation should be run on the GPU for max speed, or on the NPU for minimum power, or on CPU for necessary sequential control, that is where the next major performance battles are going to be fought. It's heterogeneous computing in its purest form.
All right, theory is great, but let's make this concrete. Let's make it relatable. Our source material uses the very demanding scenario of video editing, which I think perfectly illustrates how all three of these processors have to cooperate in a high-demand application to prevent that frustrating lag and latency we've all felt.
Oh, video editing is a phenomenal laboratory for heterogeneous computing. It's perfect because it involves complex user management, massive high-throughput data processing, and now, increasingly, these specialized intelligence features all running at the same time.
Okay, so let's visualize this workflow. I open my video editing software, let's say it's Adobe Premiere or DaVinci Resolve, and I import my big high-resolution clips and I start scrubbing through the timeline. What is the CPU doing during that initial high-demand but often very sequential task?
So the CPU's role here is pure management. It's coordination. It's handling the operating system's interaction with the application itself. It manages the entire application interface, all the buttons, the menus, the drag and drop actions.
The UI.
The UI. And more critically, it's controlling the timeline. It's ensuring that when you hit play, the audio streams are synced up perfectly with the video frame rate and that all the various layers of video are stacked in the correct order. It's handling the overall workflow coordination. It is the director of the entire production.
So the CPU makes sure the application runs correctly and it manages the sequence of events. But the moment I start applying, say, a complex color grade or I add a heavy transition effect, that's when the factory floor, the GPU has to kick in.
Absolutely. The second you apply a demanding filter or effect, that is a parallel problem just waiting to be solved. The system suddenly needs to process millions and millions of pixels per second, calculating lighting changes, blurs, saturation, complex compositing.
It's a massive parallel math task.
It is. So the GPU is what's accelerating the rendering and executing those effects. It takes those raw video frames and applies the filters and effects you've chosen simultaneously across the entire image dataset.
And this is why, if you're using professional software, but you have an insufficient GPU, rendering just a few minutes of video can take hours.
Oh, easily. The CPU is basically just sitting there waiting patiently for the GPU factory to finish churning through all those calculations.
What about just seeing the preview on the screen?
That's the GPU too. It's crucial for the display itself. As you scrub back and forth on the timeline, the GPU is responsible for rendering that preview window in real time. It's quickly fetching data from memory, applying temporary effects on the fly, and pushing that image buffer to your screen so you get that smooth, low-latency visual feedback.
Something that would just bring a sequential CPU to its knees.
Completely.
Okay, so now here's where the NPU, the modern specialist, enters the picture. Depending on how sophisticated my editing software is, the NPU is going to handle very specific, intelligent features that rely on a pre-trained AI model.
Exactly. The NPU is focusing on tasks that are mathematically heavy but require minimal power and are really optimized for those low-precision tensor operations we talked about. For instance, if the software includes AI-driven background masking.
Like rotoscoping, but automatic.
Right, where it isolates the subject without a green screen. That often runs on the NPU. It's running what's called a segmentation neural network model that requires constant low-power inference on the video stream.
What about noise reduction? We see a lot of software now using deep learning to automatically clean up grainy footage or noisy audio.
That's an excellent example. The AI model that analyzes the visual or audio noise profiles and then intelligently subtracts that noise while trying to preserve the detail, that optimization is absolutely perfect for the NPU.
Or automatic captions.
Automatic caption generation, perfect. The model that processes the raw audio and converts it into predicted text is highly optimized for the NPU's specialized math. It allows for real-time transcription. Another classic feature is video upscaling, taking a 1080p video and enhancing it to 4K resolution using generative AI models to intelligently fill in the missing pixel data.
Okay, so if we trace the complex path of just a single action, let's say I apply one of those AI-driven noise filters, the interconnectedness becomes crystal clear. My click is managed by the CPU, which tells the application that a noise reduction module needs to run.
Right.
The CPU then prepares the data and hands it off to the NPU. The NPU runs its highly efficient, low-precision tensor model to calculate all the new, cleaned-up pixel values. Once it's done, the NPU hands that processed data back to the GPU to be layered correctly into the final render pipeline,
Right.
which the CPU is still coordinating the whole time.
That is the perfect illustration of interdependent specialization. It clearly proves that these specialized chips are now entirely dependent on each other. If the CPU bottlenecked the instructions, or if the NPU couldn't process the enhancement fast enough, or if the GPU couldn't handle the final rendering throughput,
The whole system grinds to a halt.
the whole experience slows down. The system is only as fast as the weakest link in that particular highly specialized workflow.
And this leads us to the final and maybe the most important, hidden challenge of modern computing. This entire conversation, we've focused on how fast these chips can compute, how quickly they can execute instructions or crunch numbers. But our source material introduces this critical final nuance, a key concluding thought that forces us to look beyond just the silicon processing itself. Hashtag 4.1, the hidden variable in speed.
This is, I think, perhaps the most practical and often the most frustrating takeaway for the average user. Performance isn't only about how fast the chip computes, it's about a hidden variable that is often called the memory wall.
The data access problem. The sources really highlight this crucial secondary factor. How fast can the chip actually access the data it needs to work on?
Just think of it this way. You could have the most brilliantly optimized general manager in the CPU, the fastest parallel factory in the GPU, and the smartest specialist in the NPU. But if the data they need to work on, the raw footage, the spreadsheet values, the matrix weights for the AI model, if all that data is sitting on the other side of a slow, single-lane road,
They just sit there waiting.
all those brilliant processors spend most of their time just idling, waiting for the delivery truck to arrive.
So the processor's brilliant, but it's hungry. A hugely powerful processor can still feel sluggish. It can exhibit high latency if it's constantly waiting for memory access, if it's not being fed with data. All of that theoretical computation power just goes completely unused.
It's a phenomenon known as being memory-bound or I/O-bound. And the problem is amplified by the sheer mind-boggling speed of modern silicon. A CPU core can execute operations in a fraction of a nanosecond. But fetching data from the main RAM, the DRAM, can take tens or even hundreds of nanoseconds.
That delay is an eternity to a processor.
It's an eternity, and we deal with this massive gap through what's called the memory hierarchy.
Okay, let's dive into that hierarchy, because this is where the speed of the data logistics team becomes, in some ways, more important than the speed of the processing team itself.
At the very top of that hierarchy, you have the registers. These are essentially tiny bits of memory built right into the core itself. Access is instantaneous.
Right.
Just below that, you have the L1 and L2 caches. These are ultra-fast, very expensive, and very small blocks of memory that are physically located right next to the processor core. The CPU, as we said, relies heavily on this massive complex cache system to make sure its complex sequential tasks are fed instantly. If the data it needs isn't in the cache, the CPU stalls.
And if there's a cache miss, the CPU has to go to the next level down in the hierarchy, which is the main system RAM, the DRAM.
And that introduces a measurable, painful delay. And if the data isn't even in RAM, well, then the system has to go all the way down to retrieve it from the slowest component of all, the storage drive, whether it's an SSD or an old hard drive.
And the challenge for the GPU is a bit different, but it's just as constrained by this, right?
It is. The GPU doesn't care about the latency of a single piece of data as much as the CPU does, but it cares deeply about massive bandwidth. It needs to move terabytes of textures and matrix data simultaneously to feed all those thousands of parallel cores.
So it needs a huge pipe for data.
A giant pipe, which is why the GPU typically relies on very high bandwidth, specialized memory. You'll see it called GDDR or HBM. That's often integrated directly onto the same package as the GPU itself, just to minimize the physical distance the data has to travel.
So to put it simply, the CPU is crippled by high latency when it has a cache miss, stalling its intricate sequential pipeline. And the GPU is crippled by low bandwidth when it's trying to pull vast data sets through a narrow pipe, which starves its parallel factory floor.
That's it exactly. The memory subsystem can, and often does, dictate the efficiency of the entire system. When you load a huge open-world game map or you're processing a long 8K video project, the actual speed you experience is rarely dictated by the CPU's clock speed. It's dictated by that memory wall, the bottleneck in the data logistics team that sits between your storage and your processors.
That realization really puts the entire hierarchy of silicon into context. The CPU, the GPU, and the NPU, they're only as fast as their ability to be supplied with data fuel. If we fixate only on the processing power, we are literally missing half of the performance equation.
And this point, I think, directly connects the whole discussion back to the listener's immediate experience. We've all used a computer that, on paper, seemed to have great specs, a fast CPU, a powerful GPU, but it still felt sluggish when multitasking or loading large files.
All the time.
And often, that poor real-world performance isn't explained by the processing power being slow. It's explained by the memory being too slow, or the cache being insufficient, or the memory bus just not having enough bandwidth. The processor is operating brilliantly, but it's operating on an empty stomach.
It seems like the true measure of modern performance isn't just MIPS or floppy-s, millions of instructions or floating point operations per second. It's also the efficiency of that data pathway. #tag outro.
So we've successfully navigated from that old single-brain myth to the new reality of the specialized silicon team and the critical data delivery challenge they all face. I think it's worth briefly recapping the distinct roles and strengths we uncovered today.
Absolutely. The CPU is our manager. It's handling the sequential logic, the low latency, and all the varied, unpredictable workloads of the operating system. And it relies heavily on large, fast cache to avoid those costly pipeline stalls.
Then you have the GPU, which is the parallel factory. It's designed for massive simultaneous throughput operations like rendering, simulation, and large-scale data processing. And it relies on massive memory bandwidth to feed its thousands of hungry cores.
And finally, the NPU, the AI specialist. It's highly optimized for low-power tensor math, enabling that energy-efficient, high-speed on-device intelligence using lower precision arithmetic.
And the overarching lesson really is that performance is a collaborative effort. It's measured not just by raw clock speed, but by the efficient flow of tasks and data between these specialists. If the system is heterogeneous, its performance is going to be defined by its weakest point of interconnect.
Okay, so here's our final provocative thought for you, the listener, and it builds directly on everything we've just explored. If these specialized processors are only as good as the data they receive, what infrastructure is actually deciding, moment by moment, if your computer feels fast or if it feels sluggish? Which component, when it's bottlenecked, causes the most user frustration?
That hidden system, the one that governs how quickly data gets from your storage all the way to the processor, that is the memory hierarchy. It's that crucial interplay between the registers, the cache, the RAM, and the deeper storage layers. That infrastructure is what dictates whether the manager and the factory floor remain constantly busy or if they're just stuck perpetually waiting.
Understanding that logistics team is the true shortcut to understanding computing bottlenecks.
It really is.
We'll leave you to mull over that hierarchy and the efficiency of data logistics the next time you open a demanding application.
Thanks for diving deep with us.
And we'll see you next time as we explore that exact hidden system that decides data access speed, the memory hierarchy, and why latency is always the enemy of speed.